Hi there, Miss Barber here. This lesson is titled Derivative Techniques, and in particular we will look at constant rule and power rule. In this lesson you will learn some of the many rules of differentiation. These techniques allow us to obtain derivatives without using the limit definition of the derivative. But first, let's review the exponent rules from algebra. Rules of exponents. Provided for you is a table that consists of the 8 common rules or properties of exponents. This table consists of 3 columns and 9 rows. The first column just lists the number for each property. The second column is titled property, and it actually lists the property of the exponents. The third column provides for you an illustrative example of that property. Let's quickly go through each of them. Rule 1. X to the power of n is equal to the product of x multiplied n times. To make it concrete, consider x to the power of 4. That means x times itself 4 times. Rule number 2. A to the power of x times a to the power of y is equal to a to the power of the sum of x plus y. Consider the example, 7 squared times 7 cubed. 7 squared means 7 times 7. 7 cubed means 7 times 7 times 7. Notice that there are 5, and that product is equal to 7 to the 5th, which we could have just as easily gotten by adding the powers. Rule number 3. A to the power of x divided by a to the power of y is equal to a to the power of x minus y. Consider the example, 9 to the 5th divided by 9 cubed. You can expand 9 to the 5th as 9 multiplied to itself 5 times, divided by 9 cubed as 9 multiplied to itself 3 times. 3 9s cancel, leaving 2 9s in the denominator, which gives you the result of 9 squared, which you could have just as easily gotten by performing the subtraction 5 minus 3. Rule number 4. The quantity a to the power of x all raised to the y is equal to a to the power of the product of x times y. Consider the illustrative example, x squared quantity raised to the power of 3. The raised to the power of 3 means x squared is multiplied to itself 3 times. So you have x squared times x squared times x squared, the result of which is x to the 6th. Rule number 5. The quantity a times b raised to the power of x is equal to a to the power of x times b to the power of x. Consider the illustrative example, quantity 2x raised to the power of 3. When expanded, that is 2x times 2x times 2x. You can separate the terms and you end up with 2 cubed times x cubed. Rule number 6. We take it as fact that a raised to the 0 equals 1. For clarity, consider if you have the ratio of x to the 4th divided by x to the 4th. If you apply the rule number 3, you would have x to the 4 minus 4, which gives you x to the 0. Furthermore, x to the 4 over x to the 4 cancel, which also gives you 1. Let's look at rule number 7. A to the power of negative x is defined as 1 over the power of a to the x, which is also equal to the quantity 1 over a to the x. It is important to note that the negative in the exponent never changes the sign of the number. And you might want to consider if you have x to the 5th times x to some power, and that's equals to 0, what should that question be? What should that power be? And finally, rule number 8. A to the power of the ratio n divided by m in radical notation is the mth root of a to the n, and consider the example, a to the power of 4/5 is rewritten as the 5th root of a to the power of 4. Example 1.7.1. Write x to the 3/4 in radical form. Applying the rules from the previous table, we can write this as the 4th root of x cubed. Example 1.7.2. Write x to the negative 2/5 in radical form. There are several different ways in which we can approach this. I am inclined to first get rid of the negative in the exponent, so we will write x to the negative 2/5 is equal to 1 over x to the positive 2/5. And then we'll express the rational exponent in radical form, so it'll be 1 divided by the 5th root of x squared. Example 1.7.3. Simplify the following expression. Write the answer in the form a times x to the p plus b times x to the q without using radicals. The expression is, in the numerator, the cube root of x squared plus 14 divided by, in the denominator, 2 times the cube root of x. In solving this problem, let's first express this expression without any radicals. So I'll write solution and begin by writing the cube root of x squared as x to the power of 2/3 plus 14 divided by, and then in the denominator, 2 times x to the power of 1/3 for the cube root. Now let's separate the fractions. This would be equal to x to the 2/3 divided by 2 times x to the 1/3 plus 14 divided by 2 times x to the 1/3. Let's proceed. Using exponent properties, we'll begin with the first term. So let's write. We'll have the 1/2 stays as the constant, x to the power of 2/3 minus 1/3. And then for the second term, we will have 14 halves. And then we still have, let's see, x to the negative 1/3. One more round of simplifying, and we will get 1/2. X to the 2/3 minus 1/3 is 1/3. Plus 14 halves would be 7. Then we still have x to the 1/3. Oh, I'm sorry, x to the minus 1/3, and we're done. Derivative notations. If y is a function of x, that is, y equals f of x, then the derivative of y with respect to x may be denoted as dy over dx or d dx f of x. These two are commonly called Leibniz notation, or f, it looks like an apostrophe but is pronounced prime, f prime of x. By the way, this has nothing to do with prime numbers. It is just called prime, or y prime. To evaluate the derivative function at a particular x value, such as at, say, x equals 2, we use the notation f prime of 2, or dy over dx with a straight vertical bar to the immediate right, and x equals 2 as a subscript, or y looks like an apostrophe but is read prime, y prime of 2. Learning tip. As with limits, we will also have many techniques and rules for differentiation, all of which you will need to know by heart. To facilitate this, make a single sheet that lists all of the rules on it, or also make flashcards of each rule with the name of the rule on one side and the formula and an example of the rule on the other. The derivative of a constant rule. If y equals f of x equals c, where c is a real number, then f prime of x, which is dy dx, which is y prime, is equal to 0. That is, the derivative of a constant is 0. This should be the first rule on the list of derivatives you are making to memorize. Example 1.7.4, find the derivative of y equals negative 17. Y equals negative 17 is constant, and so according to the derivative of a constant rule, the derivative we write as y prime is equal to 0. Let's observe that if you were to graph the function y equals negative 17, that would be a horizontal line. So we would write y equals negative 17 for the horizontal line with the understanding that it has a y-intercept of negative 17. Horizontal lines have a slope of 0 that is consistent with if we take the derivative of a function that represents a horizontal line, it would be 0. Example 1.7.5, use binomial expansion and the limit definition of the derivative to find the derivative of f of x equals x to the fourth. One of the tools we are able to use is something called Pascal's triangle, which corresponds with a binomial expansion. For example, if you do x plus h quantity raised to the power of 0, anything raised to the 0 is 1, and that matches with the tippy top point of Pascal's triangle, which is 1. If we do x plus h to the power of 1, that's just 1x plus 1h, and let's observe that in the second row of Pascal's triangle we have 1 and 1. Now let's look at x plus h quantity squared. That is equal to x plus h times x plus h, and when multiplied out we'll get x squared plus 2xh plus h squared. Now let's superimpose those coefficients onto the Pascal's triangle, and we see 1, 2, 1, and multiplied out. Again, x plus h quantity squared is 1x squared plus 2xh plus 1h squared. Let's consider x plus h quantity cubed. That is actually x plus h times x plus h times x plus h. And using Pascal's triangle, we are able to glean that the leading coefficients are 1, 3, 3, and 1. Let's observe that we get the 3 by adding the 1 and 2 together in the row above. And again, for the second 3, we get that by adding the 2 and 1 together in the row above. Using those coefficients, we can expand the x plus h quantity cubed to 1x cubed plus 3x squared h plus 3xh squared plus 1h cubed. And finally, at x plus h to the fourth. That means x plus h times x plus h times x plus h times x plus h. We could cumbersomely multiply that binomial out 4 times or use the pattern from Pascal's triangle. The coefficients are 1, and then the sum of the two numbers above, 1 and 3, gives us 4 for the next coefficient, and then 3 plus 3 gives us the 6, and then 3 plus 1 gives us the 4, and then of course 1. Using 1, 4, 6, 4, 1 as the coefficients for x plus h to the power 4 expanded, we get 1x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus 1h to the fourth. Let's use that expansion in the limit definition of the derivative. That is, the limit definition of the derivative, if you will recall, as f prime of x equals the limit as h approaches 0 of f of the quantity x plus h minus f of x divided by h. Now let's consider this for f of x equals x to the fourth. Then applying the limit definition of the derivative, we get f prime of x equals the limit as h approaches 0 of, and then gleaning from the previous page using Pascal's triangle, the quantity x plus h to the power 4 is 1x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus 1h to the fourth minus, and f of x is just x to the fourth. Let's observe that the x to the fourth cancel, and in the remaining terms of 4x cubed h plus 6x squared h squared plus 4xh cubed plus 1h to the fourth, there is a common factor of h, so let's factor that out, and the expression becomes the limit as h approaches 0 of h times the quantity 4x cubed plus 6x squared h plus 4xh squared plus 1h 1 times h cubed. Continuing, the h in the numerator and the h in the denominator cancel, so now we still have the limit as h approaches 0 of 4x cubed plus 6x squared h plus 4xh squared plus 1 times h cubed. Let's take the limit. That is, replace each h with 0. So in the next line, we don't write the limit as h goes to 0 because we have let h go to 0. That gives us 4x cubed plus 6x squared times 0 plus 4x times 0 squared plus 1 times 0 cubed. The last three terms go to 0, and we're able to conclude that the derivative of x to the fourth is equal to 4x cubed. Let's observe. We know that if f of x equals c a constant, then the derivative f prime of x for c is 0. If f of x equals x, which is a line, then the derivative f prime of x equals 1. We have computed previously that if f of x equals x squared, then the derivative f prime of x equals 2x. And if f of x equals x cubed, then that derivative f prime of x equals 3x squared. We just computed with the previous example that if f of x equals x to the fourth, then f prime of x equals 4x cubed. At least with the last two examples here, we see a pattern. It appears that the power, when you take the derivative, becomes the coefficient, and the power decreases by 1. When we apply the rules of exponents to f of x equals c, to f of x equals x, and to f of x equals x squared, we see that this power rule also applies when taking derivatives. Let's first consider f of x equals x squared. Well, the derivative f prime of x would be, bring the 2, which is the power, write it down as the coefficient. So you have 2 times x to the power of, the existing power is 2, minus 1, which would be 2 times x to the power of 1, which gives us the 2x, the derivative we have previously computed. Now let's look at f of x equals x, which can be written as x to the power of 1. So when we take the derivative f prime of x, that would be equal to, write the power as a coefficient, 1 times, and then x to the power of the existing 1 minus 1, which will give you 1 times x to the power of 1 minus 1 is 0. We remember from the rules of exponents that x to the 0 is just 1, so when computed, the derivative of f of x equals x is 1. Using the general power rule. Now let's try that for the constant. If f of x equals c, we know that c is equal to c times 1. 1 doesn't change anything when it's multiplied, and using rules of exponents, we know that x to the 0 is 1, so we will replace the number 1 with the notation x to the 0. That is, f of x, which is equal to c, can be written as c times x to the power of 0. Now let's apply the derivative rule, the general power rule that is. So the derivative f prime of x is equal to, we leave the c, which is the constant, alone, times. Bring down the power, which is 0, and write that as a coefficient. So 0 times x to the power of 0 minus 1. Any set of factors where one of them is 0, the product is 0. And so we get that it is consistent. F prime of x equals c. The derivative is 0. The derivative of a power function rule. If y equals f of x equals x to the n, where n is a real number, then the derivative denoted by f prime of x, or dy dx, or y prime is n times x to the power of n minus 1. From now on, we'll use the rules. It is no longer necessary to use the limit definition of the derivative. Example 1.7.6. Find the derivatives of the following functions. A, f of x equals x cubed. We will use the power rule. To find the derivative, we write f prime of x equals. We bring the 3 down to make it a coefficient. X to the power of 3 minus 1, which would be a power to 2. So the derivative, f prime of x, is 3x squared. Part B, g of x equals 15 pi. Let's note that pi is a constant, so 15 times pi is still another constant, and we know that the derivative of a constant, we'll write g prime of x, is equal to 0. And finally, part C, y equals x. When we take the derivative, we recall that y prime is equal to, and the derivative of x. Let's continue with part D. H of x equals 1 over x to the 6th, which can be written as x to the minus 6th. That's the form we needed in order to use the power rule. To find the derivative, we have h prime of x is equal to negative 6, we bring that down and write it as a coefficient, times x to the power of negative 6 minus 1, which would be negative 7. Part E, y equals the 5th root of x. We must first rewrite that so that we have an exponent. So the 5th root of x is x to the 1/5, and then we can apply the power rule. So y prime is equal to, write the 1/5 as the constant, x to the power of 1/5 minus 1, and that'll be negative 4/5. As a quick reminder to do the subtraction 1/5 minus 1, you would write this as 1/5 minus a common denominator for 1, which is 5/5. The common denominator, 1 minus 5, gives you negative 4, denominator of 5. Then let's do part F. Y equals 1 over x. Using the rules of exponents, we would re-express this as x to the minus 1. Now we're ready to take the derivative. Y prime is equal to, write the negative 1 as a coefficient, x to the power of negative 1 minus 1, would be negative 2. That is a perfectly acceptable way to express your answer. If you did not want negative exponents, you could have just as easily written it as negative 1 over x squared.